Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Sam Moulton from the Business Review, and I will be your host. I'd like to welcome you to our new webinar platform, On24. You'll notice that this webinar is browser-based, so if you disconnect, please click the link you received by email to rejoin. If you require any assistance at any point, please use the yellow Help widget and click on the green Resource List widget. You'll find a poster on today's subject that you can view or download, and some Freeslate and Wyatt URLs. Today you will hear presentations on 2 automated solutions to evaluate the robustness of your Biologics formulations. We are pleased to have Dr. Russell Burge from Freeslate and Dr. Daniel Sum from Wyatt Technology joining us today. Time permitting, we will conclude today's webinar with a brief question and answer session. Before we begin, let me invite you to submit your questions using the questions widget on the upper left-hand side of your audience console. In the questions window, type in Russell or Dan's name before your question and then press the submit button. Any questions that we don't have time to answer will be answered privately in follow-up email messages from Russell or Daniel. Our first speaker today is Dr. Russell Burge. Russell earned a Bachelor of Science degree in Biochemistry from Arizona State University in Tempe. Russell obtained a PhD in Molecular Biology and Biochemistry from the Scripps Research Institute in La Jolla, California. After graduation, Russell received postdoctoral training at the University of Colorado in Boulder. During postdoctoral training, Russell worked on the biophysical characterization of RNA and DNA aptamers relevant to biopharmaceutical industry. Russell then joined KBI Biopharm as a scientist, where he worked on more than a dozen biopharmaceutical development projects. Currently, Russell is an application scientist at Freeslate. The title of Russell's presentation today is Applications of Automation for Biologics Formulation, Preparation and Stability Studies. So without further ado, please allow me to welcome Russell.
All right. Thank you very much, Sam, for that introduction. So today I'll be talking about 2 case studies where we're using Freeslate automation platforms and third-party integrated instrumentation to further formulation development of biologics. These are basically split into 2 case studies. The first case study is a plate-based high-throughput formulation screening, which is more akin to pre-formulation and early stages of formulation, and in some cases possibly developability assays and studies. The second case study, we're using the automation now to look at more relevant container closure systems with drug product. In this particular case, we're looking at vial-based stability studies. These stability studies also include elements that one would oftentimes see at possibly earlier stages of development, where we can actually look at buffer and pH screening, force degradation, and short-term accelerated stability studies in the final container closures. So this is sort of a hybrid between what you would see possibly in later stages of formulation development and also those in earlier formulation development. So the intention of these demonstrations is really twofold. One is to show the increase in the efficiency of actually collecting the data, that means performing the studies, and the other one is, the other facet is really how do we handle all of this data, and we're demonstrating that we with this automation solution, there's a high throughput data stream that comes out, and we can also handle we can manage that data as well. So really the intention here is to look at how we can design and enhance the productivity of current activities. So there won't be any exotic high throughput methods, but rather we focused on looking at what laboratories are doing currently, and we've made tools and solutions to increase that productivity. As I mentioned before, data management is a key to the success of these solutions when they're implemented. And so we integrate with multiple analytical instruments, including the Wyatt DLS instruments, which we'll hear more about later. And we also use the system to perform methods that are somewhat tedious and strenuous for the scientists and analysts, specifically formulation preparation, analytical sample preparation, and also other laborious manual techniques such as pH measurement or visual inspection. So just to give a little overview about Freeslate and the automation solutions we make for drug development, we begin with our proprietary automation platforms. So here on the top we have one of our what we call core module robots. This is a configurable automation system that has multiple modules that can be put in place that can perform not just processing and liquid handling, but also can perform analytical methods on different formulations. So that those systems are oftentimes integrated with third-party analytics, and we use the Freeslate Lab Execution and Analysis software program, the so-called LEA software suite, which allows the scientists to design the experiments and pretty much perform all of the different activities they would in the laboratory for the study. Those activities are supported by the software. And we also then couple with our and collaborate with our customers to understand what are the bottlenecks and how the automation is best suited to increase their productivity and make them successful in a rapid fashion. So how it looks sort of on paper is, on the left here, we can see these multiple areas of the study, starting from design, execute, analyze, and report. And the LEA software supports all of these phases. So for instance, with the designing of the experiments, we have the Library Studio software program, which allows us to design the experiments, processing, and analytics using a drag-and-drop based approach. So it's relatively straightforward for the scientists to understand and implement. We also provide template designs that speed up the success of our customers. We also have Automation Studio software, which basically then takes the information from the Library Studio, takes those experimental designs, and implements them such that the samples can be prepared, material can actually be processed in a multitude of different ways, and that software also will run the robotics and the third-party analytics, which also increases the productivity. And then in the end, Automation Studio sends all of that data to a singular database as part of your corporate database, and we have Polyview software, which now allows for the scientists and their managers to look at the results in real time and make decisions and create reports to disseminate across departments. So how it looks in sort of the real world is, again, we have the design to report structure here, so design, execute, analyze, and report. And what happens is we start with the scientists being able to work from the robot or possibly another site. They make the design and they send it to this database. This database not only contains the designs, but it will later contain all of the information for processing and analytical data. And what happens there is once it's part of the database, it can interact with this application server, which then networks all of the different components of the system. And as we'll see here, the scientists can later work on all of the other phases at their desk or possibly in the laboratory, and all they need to do is access that application server, and they can get the designs and they can look at the data. So to support the execution, they'll basically draw up the designs, and they'll send the commands to, for instance, the Freeslate robotics system to perform preparation of formulations or possibly stressing the formulations and also doing analytics. They can also then use the designs to send commands out to third-party analytics, which we'll talk about a little bit later. And not only do we send out the commands to those third-party analytics using the LEA software, but the data then is retrieved automatically, sent back to the Oracle database, and then the scientists can later analyze that data, find out if there's something interesting happening so they can maybe retest some things, or maybe they want to reprocess, and then of course they can take the data and report that out. And so really the idea here is you have this a multitude of different laboratory devices that are now part of a networked system, and it really allows the scientists to have more power at their fingertips because they're able to, with one set of software programs, run all of these different analytical devices oftentimes in parallel, and this can improve productivity. And the emphasis here really is that with one scientist, this whole setup, this network device, sort of acts as one large networked and automated laboratory. So how does the data look in the end? So when we run these high throughput studies, we have a lot of data. And the LIA software actually supports the formulation studies quite well in the sense that it can also manage the data and easily from the database. So once the database has been queried, you can actually go back and look at all of the data and link it back to the original vial very easily. So for instance, here we can see a dashboard, which is basically aggregate data from the vials. And on the left, you can see unique identifiers for the vials. And across the different columns, you can see the HPLC and other analytical devices that are part of these networked systems. So all of those analytical samples there have gone through some sort of processing, but now in the database, they're linked back to the original vial. This certainly increases the productivity of the scientists because they're able then to rapidly and oftentimes in an automated fashion produce these dashboards. It also allows them to very easily compare across multiple conditions because you would have a dashboard, if you will, for each of the conditions, and you can rapidly compare those. We also support making data models using DOE, so you can actually characterize and predict different behavior, and we connect with informatics such as JUMP and Spotfire. There's also the ability to export out into Excel or CSV files, and the Polyview software can also take numerical data from this data set and create plots, as we see there on the bottom right. So there are certainly some challenges in formulation development that are addressed well by automation. So, for instance, one of the problems or challenges that are posed by formulation development is the lack of or challenges with resources. So one of the things that automation can do is actually increase the efficiency of one scientist by, again, enabling this networked hardware and software unit to create increased efficiency. So essentially, the scientists can use this networked and automated laboratory as if it was one unit, and this enables one scientist to perform an entire study in a highly efficient manner. Part of the reason why we can also get increases in efficiency is not just because of that reason, but also now we have high throughput solutions that compared to these highly manual methods. So for instance, with pH, we now have a high throughput automated pH method. We have now a high throughput enhanced visual inspection method as well. So we're supporting the scientists by having the automation perform these highly manual methods. In addition, when the automation system is performing these tedious tasks, the scientists can focus on other activities that are more valuable in parallel. Another challenge is material consumption. So here we've tried to put a focus on using a low amount of material in our 96-well studies, but certainly there's flexibility for our customers and scientists to work with a broad range of different formats. Also, having that data automatically saved into one database is certainly increases productivity as well, because there's no time to look for. You don't need very much time to find the data. It's rather all there, very simply queried. And there's also the possibility of improved study results. So, for instance, there can be some subjective interpretation of certain types of assays, such as color and particles, and so visible particles and turbidity. And we have high throughput solutions now where we actually use European pharmacopoeia and NIST standards to calibrate the system. There's no need to individually label secondary containers because we can label entire vial racks with the barcodes, and we can read those and keep track of where they are. We have the ability to calibrate the system and perform system suitability checks, and these can oftentimes support highly reproducible results and can increase the confidence on how the system is performing. Notebooks are streamlined because, as you can see with those dashboard views, all of the data can be quickly aggregated, and everything that is done by the system is saved and time-stamped, even if it's moving an object from place to place or adding any kind of material. All of that is saved in the database, and that data has high data integrity because it cannot be overwritten. It maybe can be reprocessed. It can certainly have some recollection, but it can't be modified from the original form. So how do we do this? So in this particular set of case studies, we're using the Freeslate Biologics Formulation System. So it's specifically designed to support development activities for biologics. So we start with a HEPA enclosure, which is a large box here that has HEPA filters at the top, and this provides a low bioburden workspace. Inside the system on the right, we have what we're calling our core module number 1. That's a system that actually performs the preparation of formulations and analytical samples, and it can also perform high throughput pH, high throughput capillary viscometry, and high throughput enhanced visual inspection. Then on the left, in the middle actually, we have a carousel that provides space for extra consumables, extra samples, and whatnot. And it also allows for the passing of material from one side, from the right side robot to the left side robot, and we're calling that the core module number 2. And this robot is actually able to physically interact with and put plates into analytical devices such as the Wyatt DynaPro and the M2 from the SpectraMax, and other processing devices such as centrifuges and plate sealers. So you can see that this system has many different integrated capabilities, from analytical capabilities on to, at the bottom we can see in italics, some stressing capabilities. And there are also some third-party analytics that also are networked to the system but are not actually part of the physical system. So now I'll move on to talking about case study 1. As I mentioned before, this is a plate-based formulation screening study. And it basically begins by having the analyst create or generate 4 different solutions. In this case, it's the acid and conjugate bases for acetate and histidine. And then we use the liquid handling capabilities of the robotic device to draw material and put it into, as we can see here, 2 ml vials. When the robot mixes these at a certain ratio, we get now a diversity of different pHs at the same buffering strength. Now we can use high-quality water to dilute material out, and we can actually, again, use our liquid handling to move material to a 96-well plate. So now we have 48 different solutions here with different ionic strengths, different buffering strengths, and different pHs. Again, we can use liquid handling to move material to the 96-well plate such that we've created 96 different formulations with API, and in this case we're including 2 different excipients, but you can see how it would be very easy to create a very large number of 96-well plates with just a few stock solutions. So this can be done rapidly, and it's done in a fully automated fashion. Then the robotic system can take this 96-well plate and move it to the SpectraMax. And when it moves it there, it will actually automatically tell the SpectraMax to generate or measure the turbidity at sort of a T0 time. And then the robotic system draws that plate out and moves it to the DynaPro. Again, the system is told to now begin measuring the DLS. And not only are we using the DLS as an analytical device, we're also doing a temperature ramp up to 68 degrees, and we're measuring the DLS as a function of temperature increase. At the end of that temperature ramp, we have the robotics system move the plate back to the SpectraMax and gather more information about the turbidity and how it's changed. Now we can actually use some of this information to help prioritize which of the formulations are performing best, and then we can later decide which of those formulations will actually be moved on to more analytics, such as UPLC or HPLC, as in this case. So here's some example data where we see very clearly that the turbidity in the beginning is relatively low. After the temperature ramp, we can see the turbidity values are now increasing. So all of this data now is being visualized by the Polyview software as part of the LEA software package. And then we can see in the top right here, it's a plot of the radii of the peak versus the temperature increase. And as you can see, there are many different variables there as far as how the data points are being displayed. But the point here is to show that the scientists would be it'd be easy for the scientists to see which of the formulations are performing best. Because as a function of temperature, you'll see the radii will remain low. And together, the DLS together with the turbidity data will be able to provide some information to the scientists as to which of the formulations is sort of worth going forward and performing additional analytics. So this is the intention of this demonstration is really to show that using a relatively small amount of API, in this case about 48 milligrams, but much less could be used in these 96 well plates, the scientists can screen a large number of preparations, a large number of different formulations using a limited number of stocks. And the idea here is that one can actually look at many different formulation variants by making multiple 96 well plates, and one could also expose those 96 well plates to a multitude of different conditions, such as shaking, heating, etc. And again, we're showing here how we're able to use the screening data to refine further testing, meaning we don't necessarily have to do UPLC on those samples that are performing poorly. And as you can see, the Polyview supports the sort of high throughput data management. So for case study 2, as I mentioned before, we start with vials. And in this case, we're looking at sort of a different set of challenges. Again, when we start performing late-stage formulation development, one of the first things the scientists have to do are actually prepare the formulations. And in this case, we're using the system to formulate or prepare the formulations using liquid compounding, both with air displacement and positive displacement capabilities of the system. We can use the system as an aseptic environment because of the HEPA enclosure, and we can basically create sterile solutions, move them in to the system, and now we've created a sterile drug product in relevant container closures. So one of the challenges often that happens is because of resource issues and oftentimes material issues, material consumption issues, not that many different conditions can be screened necessarily, especially early on. So the intention here is to show how the automation can possibly support looking at a larger number of formulations in a relevant container closure in more conditions, possibly earlier in drug development. So again, we'll see how data management is supported with the automation, which could be a challenge otherwise in laboratories. And here we can actually see how laborious methods such as visual inspection, viscosity, and pH are now fully automated using these systems. And again, because we have the ability to calibrate the system and have performance checks, there are ways to increase the reproducibility of the studies over time. So we have here in the beginning, I'm showing a bird's eye view of 2 ml vials in a 24 vial plate, and this pie chart basically shows the different components from sterile stocks that are added by the liquid handling components of the system. Those are gently mixed to create homogeneous solutions. Now there is the stoppering and capping, which does have to be manually performed, but The formulation itself is performed by the robotic system. Once they're sealed, we can actually take those, the robotic system will draw those vials into the visual inspection station where color, turbidity, and visible particle analyses will be performed. Each one of those analytics can be calibrated, as I mentioned before, and we'll see some examples of that data. After that so this is just an example of how we perform this workflow, as we call it, but there certainly is some flexibility here. We can then unstopper and unseal those vials, use those liquid handling capabilities to draw the material out into 96-well plates or vials, and now we can perform pH and viscosity serially. So here we have a high-throughput pH meter. It has a 4-tip pH probe that is solid state and can go through and measure an entire 96-well plate in about 48 minutes. And then we have the high-throughput capillary viscometer that can measure viscosities of samples up to 100 centipoise. So all three of these analytical devices, which constitute 5 different methods, are all proprietary technologies of Freeslate and are part of the core module systems. Now we can take material from that original 96-well plate and use it to create 2 different plates that now can be run in parallel. So one plate can be used to do UV and DLS, and then another plate can be moved off to, in this case, we performed reverse phase and SEC HPLC. So as you can see here, this constitutes 9 different analytical devices and analyses that can be performed starting from the drug product in the beginning. And the way this looks is when the scientist goes to perform the T0 testing after formulation is completed. So here's a sort of a data-rich table which just shows you just a part of the T0 testing. The time in which it takes is only about 6 to 9 minutes per formulation. That includes aliquoting and doing the analysis because the automation is supporting so much of that. So really the idea here is that one scientist can actually perform all the T0 testing, meaning all 9 analytics, in a single day. Some of those analytics are simply initiated, but would require no more attended labor until they were actually finished. So it's important to note here that this is just the T0 testing. We created enough drug product in the vials in this particular case to look at 3 different stress conditions. So here now on the next slide, we can start to look at the different, looks like I actually need to go back one. We can start to look at the different analytics. So in this case, we're looking at visible particle counts across the 4 different conditions. So as you can see here in red is our T0. In green is the freeze thaw. So we've performed freeze thawing off of the system. But in magenta here, we actually subjected these vials to agitation on the deck. So on the same deck where analysis is being performed and the formulation was performed, you can also stress the samples. And the same with the heating. In cyan here, we can see data from those vials that were actually heated on the robotic deck. And what we can see is that initially the visible particle counts are relatively low, but then we can start to see some diversity in the behavior and in the robustness of the formulations as a function of heat. Same goes for turbidity. So again, we can see at T0 and at agitation, with agitation, we see relatively low NTU units. So these are the nephelometric turbidity units that we can use we have standards to calibrate this, and we can actually run a calibrated analysis on the turbidity. And we can see that after freeze thaw, perhaps there's a slight increase in the turbidity, but after this heating ramp, we certainly see a diversity in the different levels of turbidity. With the DLS data, we also see some diversity. Here we see actually with the low pH formulations, which are highlighted with these gold ovals, we see that in the case of sometimes freeze thaw, but certainly agitation and heating, we start to see polydispersity increase with those formulations, which is suggesting a difference in robustness between the different formulations. Our reverse phase HPLC data is highly consistent with our SEC data, and both of them show that the protein begins highly pure and maintains its purity across all formulations and across all stressing conditions. So then if we're looking at the conclusions for just the data here for this second study, we're using BSA as a proxy protein, but we can see that the differences in the formulations appear to be independent of the BSA stability. So for instance, when we look at the turbidity and the visible particles, we can see that many of the formulations had significant increases after stressing. It's not shown here, but we do have an app note that is available from freeslate.com, which shows the color data. And in that case, upon heating, those formulations with histidine have significant increases in the tint. And so, again, we're seeing some changes in the formulations. And with the DLS, there is some data suggesting that there's heterogeneity of those peaks, especially correlated to the low pH formulations. But when we look at the HPLC data, and we can provide those chromatograms for anybody who's interested, we can see that very clearly that the protein maintains its purity across all the formulations. And this is really suggesting that many of the stability factors that we're seeing, or stability indicators we're seeing in this study, can actually are likely to be traced back to non-protein components of the formulation. So really where we're interested here is adding productivity and efficiency to laboratories. So from our experience as formulators, when we compare using the automation and using highly manual methods, we see about a 4 to 6 times increase in efficiency compared to manual methods. And what this means is basically if we're comparing attended labor for attended labor. So simply stated, with using the automation, much less attended labor is necessary. So to give you an example, in this particular case, looking at all of the activities, including of preparation of the formulation, preparation of the samples, the analysis, and the reporting, all of these different components required only 28 hours of attended labor for one scientist for that entire study. This does not include certain aspects of the studies that simply will take the same amount of time, whether it's manual or automated. So if we kind of break that down, one of the important parts there is also performing the formulation. So we made 192 different formulations in the 2 ml vials. And that took about 6 to 8 hours, but really only about 2 to 3 of those hours were attended labor, and much of the strenuous and tedious work was actually performed by the automation in this HEPA enclosure, and in the meanwhile, the scientists can move on and do other activities in parallel. So what's important to note here for comparison is that if we include all of the preparation time, analysis, and notebooking and report generation, we can approximate about 8 to 10 minutes per formulation to perform all 9 analytics, which is about 6 to 8 hours for 48 different formulations. And this does not include certain acquisition times, nor does it include the times necessary to stress the samples. But the idea here is that there are increases in productivity thanks to the automation. So there are some other advantages as well, sort of wrapped into this generalized idea of increased productivity. So for instance, we have the ability to look at perhaps a broader range of conditions than normally would be screened because of the increases in efficiency. There are these hopes and designs that the material consumption can be relatively low, but in certain cases, scientists may actually want to look at larger amounts of material, and that does happen with automation as well. The automation is able to eliminate these subjective interpretations of assay results such as color, visible particles, and turbidity because we actually have these NIST and European pharmacopoeia standards. We can see that there are, as I mentioned before, there are certain procedures that can be performed to ensure the reproducibility of the results. And in this case, there are some possibilities of having increases in reproducibility compared to highly manual operations. And what we see is because all of the actions are saved in one database, it makes it it keeps the data integrity at a very high level, and it makes it very easy for the scientists and their managers to query those databases and create customized reports rapidly. And because of that, there's time savings, but there's also just simply the ability to manage the data and make informed decisions rapidly. And really, the idea here is for the scientists to use the automation system now to perform the menial and tedious tasks that the automation is very well suited for, while the scientists can move on, understand the data, possibly refining their formulation studies, and basically creating a better drug product. So I want to thank you for your attention. There are some people here from Freeslate I'd like to thank. And certainly I welcome anybody who's in the audience to send me an email if they have any additional questions. As I mentioned, we will have an app note that will cover the case study 1 that will be available on freeslate.com. And I'd also ask you kindly to please fill out the survey questions at the end of the webinar.
Thank you, Russell. Our next speaker is Dr. Daniel Sum. Daniel is Principal Scientist and Director of Marketing at Wyatt Technology Corporation. As Principal Scientist, he investigates techniques for characterization of macromolecular interactions, contributing to the development of new instruments and applications. As Director of Marketing, Dan believes that Wyatt's success can only be achieved through that of their users and endeavors to connect customers with the right solutions to their analytical challenges. The title of Dan's presentation today is High Throughput Dynamic Light Scattering, DLS, for Screening Biotherapeutic Formulations. And now I'd like to hand over to Dan, so over to you, Dan.
Well, thank you very much, Sam, and also I'd like to thank the folks at Freeslate for the opportunity to present today. Our products play very well together, and so it's just fitting that we also collaborate well in education and outreach. And so in the time I have in this webinar, I'll be talking about something about what dynamic light scattering does and what it's good for. As Russ mentioned, high-throughput screening is important in developability assessments and also looking at pre-formulation of biologics and final formulation. The things that we'll be using dynamic light scattering for will be to determine gross aggregation states and also assessments of stability, both colloidal stability and thermal stability. And it's also possible to use dynamic light scattering for screening viscosity. And I'm not sure that probably Freeslate has other techniques for doing that, but it's nice to be able to compare viscosity assessments. So how does dynamic light scattering work? Basically, we have molecules in solution that jitter around due to Brownian motion, as you can see in these little videos here of particles. And we shine laser light on them, and the light scatters off of these particles. And as you can see in the upper right corner, the waves from the two particles reach the detector and interfere. And as the particles move around, the phases will change, and there'll be constructive and destructive interference, leading to an intensity on the detector which looks noisy. And what we do is we analyze the noise. So the information in the fluctuations of the laser scattering signal tell us about the rates of diffusion. Basically, smaller particles will have higher diffusion rates, and larger particles will have slower diffusion rates. So we analyze those fluctuations through a technique called the autocorrelation function, and that is further analyzed to determine the spread of hydrodynamic radii in the solution. So all the particles will contribute, and we'll get some indication of the different sizes present. You can see here typical output. The technique is not a very high-resolution technique. There are other ways of addressing a high resolution that Wyatt provides, but for purposes of screening, dynamic light scattering is low resolution, but very useful because of its other properties. That is that you can perform measurements in microwell plates and very rapidly on small quantities of sample. And so you can see here that the x-axis is logarithmic, and we get molecular sizes ranging over nanometers and up to hundreds of nanometers. So we take that analysis and provide a graph. If our sample is monodisperse, that is, all the particles have the same size, then our graph of sizes will be narrow, and it'll look like this. And if there's small degrees of aggregation, which Russ alluded to earlier, then what we'll see is an increase in the width of that peak. And that increase of width is measured through the polydispersity. Polydispersity essentially means we have particles and small aggregates of those particles, and that shows up in the width, which is the polydispersity. One of the nice things about dynamic light scattering is that even without any separation step, it's possible to determine distributions of particles. It's relatively coarse. Again, it's a logarithmic scale. But if we have some small particles and some very large particles, the analysis will show that up very clearly. And so we see here two peaks, one small size, one large size. And in general, we can differentiate peaks if the particles differ in radius by a factor of 3 to 5. That's a pretty large change in mass. So these are not small oligomers that we're differentiating, but they're still fairly large oligomers, but not too large. And again, if there's polydispersity due to, say, aggregation or small distributions around each individual size, that will appear in the distribution graph, and we can see the corresponding increase in width. So here, each mode has its own polydispersity. All of these can be analyzed. The Freeslate software provides a certain amount of analysis, and then you can come back to the Wyatt software and do an additional analysis if necessary. The instrument that Russ alluded to is the DynaPro Plate Reader 2. This is an instrument which measures dynamic light scattering directly inside of the microtiter plates. So you load up the plates, and as you can see in the cartoon in the upper left corner, we shine the laser directly into the well from the bottom. Light is scattered from the solution, and it is collected by a fiber optic cable also underneath the well. And that fiber optic cable leads to a high-sensitivity detector known as an avalanche photodiode, which is used to analyze the dynamic light scattering. The DynaPro plate reader utilizes industry-standard plates. We prefer to use the higher quality plates, but in general, we have a list of inexpensive plates that can be used and disposed of and give quite good data. The range of measurement is radii from 0.5 to 1,000 nanometers. The sensitivity would be 0.125 mg per mil for lysozyme, and the sensitivity in dynamic light scattering scales with the molar mass. So, for instance, if you're looking at an IgG that has a molar mass 10 times that of lysozyme, you could measure a concentration which is 1/10 of this, that is 0.0125 mg per mil of lysozyme. The minimum sample volume, of course, depends on the well plate that you're using. It could be as little as 4 microliters if you're using 1536 well plates. More typically for the 384, which seems to be the workhorse for this, 10 to 20 microliters is typical. The DynaPro Plate Reader 2 incorporates temperature control from 4 Celsius up to 85 Celsius. And it will automatically attenuate the beam in collection so that if you have a sample which has gone turbid due to heating, it will not saturate the detector. It will adjust to accommodate that. And, of course, it also includes a software interface to robotic liquid handling systems. The Freeslate platform is probably the best example. We also include a camera. Let me just go back there. We also include a camera. And so the camera actually takes a picture of each of the well plates from beneath. And so if you have funky data coming off of one of the wells, you can go back and check the image and say, oh, yeah, you had a bubble in there, or you had some precipitation or something else was going on. So that camera turns out to be very useful. So if you're going through one of these screening processes, you might load up a well in this fashion. So a standard 384 well plate, multiple candidates, multiple formulation conditions, and some controls. And you would probably scan these wells at about 5 to 10 seconds of acquisition time per well. If you include the time it takes to move the laser head between wells, that adds up to less than 1.5 hours to scan the entire plate. So so you can get all these formulation conditions scanned very rapidly. If you're familiar with dynamic light scattering, you may be used to longer acquisition times. Longer acquisition times will give you better resolution and better sensitivity. But for the most part, when you're doing high-throughput screening, you don't need that degree of information. And the amount of information and the robustness that you get off of a 5 or 10-second scan will suffice. And so in the scan, you can look at each well, and you can look at the distribution of sizes and determine the average radii, if there are multiple modes, if there are large aggregates, like you can see in the right side of the graph, and how the polydispersity might change under the different conditions that you're measuring. So here's an example of one monoclonal antibody under 2 formulation conditions, with and without some sucrose. And you can see that prior to lyophilization, both of these exhibit monomodal behavior, so a single peak. The peak with sucrose has a slightly shifted radius and slightly higher polydispersity, and that could be due to the presence of sucrose. But after lyophilization and reconstitution, what we see is that both of these have produced some higher peaks with larger sizes on the order of hundreds and even up to almost 1,000 nanometers in radius. And you can see that there's a difference in the behavior. So the formulation without sucrose had a little bit more of the 100 nanometer particles, whereas the one with sucrose had less, but also had some larger particles up in the hundreds of nanometers. Now you notice that this graph plots on the y-axis percent intensity. So dynamic light scattering in general will output the intensity of the scattered light and how much you're getting from each of the modes and how much of the particle types. In principle, that can be reduced to percent mass. Now this is not a very accurate reduction from intensity to mass because it depends on certain assumptions, but you can get a general idea for how much mass is in the aggregates. And here we see that with all of the information that you got out of there, all the scattered light that the aggregates produced, they only accounted for a fraction of a percent or maybe a little more than 1% of the total mass in the sample. So if you were to run this through, say, the UHPLC, you would see that you have almost all monomer and very little loss. Actually, you probably wouldn't see these large aggregates. They'd be lost on the column. But in terms of sample recovery, you would see there's almost all recovered because light scattering is extremely sensitive to aggregates, and so it picks up even very small amounts of aggregates. In terms of thermal stability, so here is a temperature ramp on lysozyme. Lysozyme does not aggregate when you heat it up, but it does unfold. And you can see that unfolding process in the change in size. So if you look at measurements at each of the different temperatures, you'd see a shift in the average radius, as shown in the graph here in the inset. Transition temperatures are in excellent agreement with other techniques, like calorimetry and CD. And you notice that when temperature is held at 90 degrees, there's no increase of radius, so there's no aggregation. In fact, if you cool this down, it will revert to the size it held previously. But that's not generally true for monoclonal antibodies, which have multiple domains. And so here you can see a few different formulations, and several samples were tested at each formulation. And each formulation has a different temperature behavior, so different onset temperature and different degree of aggregation as it goes through the temperature ramp. And you can also see that when you hold it at the highest temperature, 70, the size just increases and increases, meaning that there's ongoing aggregation. And again, you can see the information provided here, the different onset temperatures that correlate very well with differential scanning calorimetry and how the average radius changes. And usefully, you can also determine what happens once it aggregates. So what I'm showing here is a different example, particular IgG at 2 different conditions, pH 9.5 I'm showing here. So when you heat it up to ADC, it forms aggregates with an average radius of 18.5 nanometers. And at different pH, 8.5, you get these very large aggregates forming. Now, if you were doing the same measurement with a different technique, say DSC or DSF, you wouldn't have this information. In fact, the aggregates that don't crash out of solution You wouldn't actually know that they aggregated via the other techniques. Finally, you can do colloidal stability studies. So colloidal stability is a measure of protein-protein interactions that cause non-covalent aggregation. And those are measured through the concentration dependence of the diffusion coefficient. So we set up several different wells in the plate with a series of concentrations. Here we're showing 3 to 10 mg per mil. And you can see how the diffusion coefficient measured by dynamic light scattering changes with the concentration. The slope of that line is given as the coefficient of concentration here, D1. And it is actually closely related to the second virial coefficient, A2, otherwise known as B22, which is a thermodynamic measure of colloidal interactions. In general, D1, or KD as it's also known, works just like second virial coefficient. If it's positive, it's generally repulsive. If it's negative, it's generally attractive. And so you can see the impact of different formulations on this degree of repulsiveness or attractiveness that indicates propensity or lack of propensity for aggregation. And finally, you can do this assessment of colloidal stability as a function of temperature. And what we see here plotted in the symbols is the points, is the values of D1. So as you go through the thermal transition, which you can see with the change in radius, which is the solid line, it goes through a negative peak, indicating that as the protein unfolds, it goes through a highly attractive state, and then as it aggregates further up in temperature, the degree of attractiveness is reduced. So that's kind of useful information telling you what happens around the thermal transition. Finally, you can use dynamic light scattering to measure viscosity, and the way that we do that is we spike in some beads of a known size, typically polystyrene latex or gold nanoparticles on the order of 50 to 150 nanometers, and we invert the equation for the diffusion coefficient in order to extract the viscosity, given that we know the temperature, we're measuring the diffusion coefficient, and we know our H of the beads, we get the viscosity. And these values tend to correlate reasonably well with first principles techniques such as capillary measurements of viscosity. And again, you can do this as a function of temperature. It's easier to set up a microwell plate with lots of different measurements and reuse them under different conditions. And so in summary, the DynaPro Plate Reader 2 is a really useful tool, probably particularly in combination with automation such as the Freeslate platform, great for screening biologic formulations. You get a lot of information out of it. You get the aggregation state. You get the propensity for aggregation through colloidal and thermal stability, and you can even measure the viscosity of high concentration formulations. If you're interested in learning more, there are some links here which will appear in the resources attached to this webinar, and they're also easy mnemonic, so I invite you to go visit those. And with that, I thank you for your attention, and we'll turn things back over to Sam.
Thank you very much, Dan. So to end the webinar, we'll now have a brief question and answer session from some of the questions you've sent in. We've got several in already, so I'll crack on with those. And the first one is to Russell. And Russell, that question is, what's the highest volume per sample prep the platform can handle?
Yeah. So normally our customers will look at relatively small amounts of material simply because most of the time material is precious. But we have actually worked with customers to go as in hundreds of milliliter scale or even larger. So really for this particular platform, so meaning the core module of this customized system that I showed earlier, really we would recommend to probably stay in the 15 to maybe 20 mLs as being the highest volume, but certainly there's flexibility to go much higher than that. And really the limiting factor is having space, appropriate space on the robotic system itself. But we do provide a lot of flexibility as far as the different formats of containers, the sizes and heights of containers. So that's really a very, I would say that's a customizable solution for our customers' needs. But suffice to say, hundreds of milliliters for this piece of equipment, and for some of our other pieces of equipment, we can go much higher than that.
Great, thank you. I'll stick with you, Russell, for the next question, which is, can the platform automate pH titration?
Yeah, so we can measure pHs on these robotic systems, and then we can add acid and base and then measure again. We can also use the system to agitate or mix the samples. But as far as automated pH titration for this particular set of systems that I mentioned earlier, we don't have that capability currently. However, we do have a system that we're working on that will hopefully be out in 2015 that will automate, among many things, pH titration of formulations.
Okay, thank you very much. Our next question is for Dan this time, and that is, what would be the best way to keep solvent from evaporating and thus leading to concentration change during DLS well plate heating measurements?
So our preferred method is capping the wells with mineral oil. It's also possible to put tape on top, though that tends to impact the optics a little bit and the data are not quite as good. Actually, I'd be interested to know how Freeslate handles that and if they can deposit mineral oil on top.
So to answer the question, we also use the mineral oil. That's right, and we've noticed, and I think we've talked to our customers who do that as well, and we're all relatively convinced that that is the best way to, at least with our system, to work with DLS to minimize the evaporation, because as we showed earlier, we had that temperature ramp up to 68 degrees Celsius, and during that particular experiment, we are using oil floating on the top, and there's very good evidence from our customers which suggests that this oil is not interfering with their formulations.
Great, thank you very much for your answers. Now back to Russell for this question, which is, can the platform automate solid dispensing?
Okay, thanks for this question. So this question takes us back to one of my earliest slides where I was talking about how the automation systems are actually somewhat configurable by moving different modules in and out of the automation system. So in this particular case, for the systems that I was talking about, they weren't configured to perform solid dispensing, but with the very same robots, if we move a few modules into place on that system, we have the ability to dispense milligram or even fractions of milligrams of solids all the way to tens, possibly even hundreds of grams of material into vials and other containers. So the answer is Freeslate has those capabilities, but for our biologics systems, we normally don't configure them so that they have solid dispensing. But what we have here also is a smaller system that we call our protege, and the protege has the ability to do solid dispensing as one of its core capabilities. So we have solid dispensing is one of those areas where there's enough interest that we actually have multiple products to support that activity.
Great, thank you. And I think one final question will go back to Dan, and that is, how much sample is required for DynaPro plate reader measurements?
Right, so again, it depends on the plate size. Our workhorse tends to be the 384 well plates, and typical fill values there would be 20 microliters, but you can definitely get good data with just 10 microliters. And that means that over the entire plate, you're going to be using less than 4 milliliters of a solution.
Thank you very much, Dan. Thank you very much, Russell, as well. That's about all the time we have for questions today. Any unanswered questions will be answered privately in follow-up emails from Russell or Dan. or to any on-demand viewers, you can still submit questions via the questions widget and they'll be rerouted on to the speakers. Before concluding today's webinar, I'd like to invite you to visit Wyatt Technology at www.wyatt.com for more information about the DynaPro Plate Reader 2 DLS system, and to visit Freeslate.com to see previously recorded webinars on the application of Freeslate's high throughput research solutions. These webinars are located in the Technical Resources section of the upper navigation menu and can be found under Learning Center. To all the attendees, you'll receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access it through our website, which is www.business-review-webinars.com. That should be up there tomorrow. We look forward to sharing further webinars with you, so please do keep an eye on our website I just mentioned. Follow us on Twitter, which is @BRWebinars for daily updates, and join our LinkedIn group Business Review Webinars. And there's one last thing you can do during today's webinar. When we stop broadcasting, a survey will pop up. You might have already filled it out, but if you haven't, a survey will pop up with some questions in there. If you could fill those out, that would be great. But yeah, that concludes today's webinar. On behalf of Russell, Dan, and myself, I thank you for attending and look forward to seeing you at future events. Have a pleasant day.